just want to point out and explain that the area underneath a force extension graph can be thought of as the work done by the spring. Now we know that the work done by the spring is equal to, we know that work done is equal to force times distance. So if I were to extend a spring by a particular distance, then that I'd have done some work on it, and the force that I would have done to extend that spring would be equal to multiplied by the distance I've extended it by would be equal to the work I've done. And therefore, that energy that I've expended would go into the spring and be stored as elastic energy. So what we can do is we can take any kind of force extension graph, and it doesn't have to be a straight line, and then we can say that this area, chop up this area into a number of rectangles, and the smaller these rectangles become, the closer they become to an accurate measure of the area underneath this curve. You can see at the moment it's not going to be perfect because that bit would be included, whereas this bit won't. You might find that they would pretty much cancel out. But anyway. And so if we just look at each individual rectangle, the width of the rectangle would be the change in the force, could be represented by a type of force applied, and the height of the triangle would be equal to the change in the length that's been applied at that point. And so the area will in fact be the work done by that. And so when you add up all these rectangles, you can see that would be the total area. So you can see it a little bit more clearly. Let's use this one because it actually is a force times extension graph. If we use just two, it says here the work is, this is a mathematical idea called integration, and it's just explaining it. But you don't do integration in A-level physics, but you do kind of use the principles. So you can see if I were to make this these rectangles smaller, it starts to approximate more and more as if it was in fact the area underneath the curve, until eventually if you have an infinitely small rectangle, then it is in fact actually the area underneath the curve or area underneath the line. So for extension, force against extension graph, the area underneath the curve really is the work done on the spring and also the energy stored within the spring, the elastic energy stored within the spring. And this becomes important because you have these graphs where you extend the spring out and then let it go back again. And when it does that, you'll have these graphs that show that they're not quite the same. I'm just going to pause the video and show you what I mean. So you can see with this graph here that if you stretch it all the way up here and then let go, it goes back again. But if you stretch it beyond this elastic limit, when you relax it again, you get this graph if you were to record the extension against the force. Now, what that is showing is that, so if I get a highlighter, originally the energy that I've put in is just going to be the area underneath this red line. But then when you go back, you can work out the area, the energy released by the spring as you let it go back, but that would be a smaller area. And so you got this area here, and this would be the energy lost, and that's going to be the energy lost as heat. And you'll only get that once it goes past its elastic limit. Otherwise, when it returns, it just returns back down the same line, and you can see that there's no difference in the two areas. So, and this links to understanding this use of the word elastic, and when we've seen it before. We've seen elastic before in momentum, or if you haven't studied momentum yet, then you'll come across it in momentum. And you get different types of collisions. You've got elastic collisions and inelastic collisions. What's the difference? Elastic collisions is when energy is conserved, kinetic energy is conserved. And so we can see here that, again, the same use of the word is coming into play. And beyond this elastic limit, when it stops becoming the extension stops being elastic, we're now not conserving energy, and we're expending some of it as heat. And so you can see this difference in energy here. So that's the energy underneath. Sorry, the area underneath a force extension graph. And when you go on to learn about stress and strain, you can also calculate the area underneath that graph. So what would that be? Well, we know that the stress is the force per area. Which, let me just turn this off. Which is the unit's going to be Newton per meter squared, or pascals if you like. And that strain doesn't have any unit. Well, according to this, the area underneath this graph is the energy stored. Now, this is the area. We won't go into the other bit. Let's just focus on this bit here. The area stored, or the work done per unit volume. Okay. So basically, why is that the case? Well, if we imagine that the work done per volume is equal to the force times distance per volume, that's going to be newtons per meter. Newtons meters divided by meters cubed, which works out to be Newton per meter squared, which is exactly what the unit of the area would be. So in a stress strain graph, the area is the work done per volume of the material, and in a graph of just of force and extension, it's just the work done. Okay.